Welcome to Fundamentals of Acoustics. Today is the last day of the third week of this course, and we will do what we will do today is continue our discussion on the wave equation, 1D wave equation, and also its solution, and we will also develop a physical interpretation for the term C. So, the agenda is some more discussion on 1D wave equation. So, what we had done in the last class was we had developed this relation okay. So, this is what we had said was 1D wave equation for pressure. What does that mean? What this means is that this equation tells us how a pressure fluctuation in air, if it is at point B A, it travels to another point in the medium. Okay. So, the left side tells how pressure will change in time at a given point, and the right side tells us how pressure is going to change in space. So, it tells us how pressure is traveling in air or in water or in a fluid media. Okay. Now, this is a partial differential equation because, and it is a second order partial differential equation, and on the left side the partial differentiation is with respect to time, on the right side it is with respect to x. So, what we will do as a first step is we will develop a solution for this. We will develop a solution for this, and we will develop a general solution for it. So, and one way to develop a general solution is to guess it. So, we will make a guess and then we will plug that guess into this equation. If that guess satisfies the equation, then it is a valid guess, otherwise our guess is wrong. So, we will say that we guess that P of x t is equal to some function f1, and that f1 does not depend on time alone, it does not depend on x alone, but it depends on t minus x over c. So, this is a guess we are making, and if this guess is correct, then when I plug f1, this definition of P back into the wave equation, it will be satisfying this wave equation, which means the left and right sides will be equal. If the guess is incorrect, then the equation will not be satisfied. But before we do that, let us see what kind of functions these could be. So, examples of f1. So, one could be x minus t over c to the power of n. This is one possible value of pressure, and I can multiply it by some constant a. Another possible function could be b sin t minus x over c. So, a and b, these could be constants, they may not be real, but they have to be constants. So, this is also of the form f1 t minus x over c. Okay. Another possible function could be c into sin n, where n could be a parameter 1, 2, 3, 4 whatever, times t minus x over c. So, these are some examples. So, all these possible functions are consistent with our definition for f1, okay, because t does not come by itself, x does not come by itself, rather t and x in this function f1 they come as a combination, and they come as in the form t minus x over c. So, these are all possible functions. Now, let us see whether this function satisfies the wave equation or not. So, if this is the case, then with respect to t, partial of p with respect to t, let us define it as f1 prime, and partial of p with respect to t second derivative is f1 prime prime. Okay. Then partial of p with respect to x is equal to what? Is equal to f1 prime into minus 1 by c, and partial of p with respect to second derivative with respect to x is 1 by c square times f1 prime prime. So, I plug this here, and the second derivative of pressure in time here, and then what I get is finally, so putting f1 in wave equation, we get f1 double prime equals c square times 1 over c square f1 double prime, or f1 prime prime equals f1 prime prime. So, what we see is that any general function of form f1 t minus x over c, so we can say thus any general function of form f1 t minus x over c satisfies 1D wave equation. Any general function. So, which means that our guess that p of x and t is equal to f1 t minus s is a correct guess. It may not be the only guess possible, but it is at least one guess which is correct and it satisfies the equation. So, this is one. We make another guess, guess 2. And here we assume that p of xt is equal to another function f2 x plus t over c. Okay, so this is the second guess. And if we do the same mathematics for this also, we find f2 satisfies equation, and I will number this equation, I will call this equation A. So, equation A. So, f2 is also valid solution. It is also valid solution. Okay. So, and then we can try guessing others, but we will find that we would not be able to figure out any general function beyond these two which satisfies the pressure wave equation. So, in general, pressure equals f1 t minus x over c plus f2 t minus x over c. So, f1 could be a series of functions by itself, right. F1 could be all types of sines, cosines, squares, as long as t minus x over c comes as a unit, and f2 could be by itself a series of functions, but this is the general solution. So, this is equation B. Now what we do is consider special case when f2 equals 0. So, in that case P of x t equals f1 t minus x over c. So, now what we are going to do is we are going to interpret the meaning of this term c and what it implies. So, we are going to consider the special case when f2 is equal to 0, then p of x and t is f1 t minus x over c. We have seen that f1 satisfies the wave equation. So, I can write t equal to f1 t minus x over c. Okay. And let us imagine a scenario So, imagine a scenario we measure p x t at x is equal to 0, t is equal to 0. What does that mean? Suppose there is sound travelling in a tube, it is a 1D system. So, at the beginning of time when we start making recordings, that is t is equal to 0, we record the pressure at the beginning of the tube which where x is 0 and initially we measure it. So, time is also 0. So, t of 0 is equal to f1 and what is the value of time? 0 minus 0 by c. So, it is equal to f1 of 0. So, in that tube, so consider a tube and sound is travelling like this. So, here x is equal to 0. So, we are measuring time at time t is equal to 0, the pressure is f1 of 0. Okay. Now, we will see what happens after time t. Okay. So, at t is equal to 1 second, at t is equal to 1 second, t minus x by c, okay. And suppose t minus x by c is 0, then when t is equal to 1 second, then x is equal to c. Okay. So, this is x is equal to c. So, what I am saying is that at x is equal to c and at time t is equal to 1 second. So, here t is equal to 0. What is the pressure here? F1 0. At time t is equal to 1 second and x is equal to c, what is the pressure here? I have to put t is equal to 1 in this, x is equal to c here. So, it is F1 0. Okay. So, we make a table. Time x so, in the beginning time is 0, x is 0, t minus x over c is 0, this is at point A, at this point. Then after 1 second, time is 1 and let us see what is the value of and at x is equal to c, t minus x over c is 0 and this is F1 over 0. Then after 2 seconds, and distance 2c. T minus x over c is still 0, f1 0. So, now let us interpret these data. So, let us call this point A, let us call this point B, and let us call this point C. Okay. So, what does this mean? Initially at time t is equal to 0, let us look at point A in this picture. At point A in this picture, the pressure was F1 0 at time t is equal to 0. At time 1 second, the pressure was F1 0 when at location x is equal to c. Okay. And at time 2 seconds, the pressure was F1 0 at location x is equal to 2c. Okay. So, what that means is that this pressure which was initially at the origin became the pressure at point B after 1 second, and this B was located c distance away, and then this pressure travelled to point C which was at time 2 seconds, which is located 2c distance away. So, in each second this pressure is moving by a distance c. So, in each second pressure moves by distance c meters, which means thus speed of sound is c meters per second. Okay. So, this is the first thing. So, one is c represents speed of sound. Second, f1 t minus x by c, this function, it represents that sound is moving in the positive x direction, because sound is moving in this direction physically. So, f1 t minus x over c represents wave travelling in positive x direction. And third is, and similarly we had another solution f2, which is t plus x over c, it represents wave travelling in negative x direction. How do I say that? I say that based on this table here, if I do the same, if I construct the same table, but instead of t plus minus x over c, I replace it t plus x over c, we will see that this function represents the wave travelling in the reverse direction. Physically what it means is that when I am talking in a room or in a pipe, when I speak, there is a wave which is travelling in the positive direction, but it could also happen that if the tube is closed at the end, then when the wave hits it, some of the wave can get reflected. So, some wave is travelling in the positive direction and some wave is moving in the negative x direction. So, these are the three important conclusions from today's discussion. First is c represents the speed of sound, and it confirms and its value which is calculated theoretically, which is c equals gamma p naught over rho. This theoretical value is pretty close to the experimentally observed value which we had discussed in the last class. The second thing is that the solution of any wave propagation equation in one dimension can be represented either as f1 or f2. f1 t minus x over c, it represents a wave travelling in the positive x direction. f2, which is a function of t plus x over c, it represents a wave travelling in the negative x direction. So, with these three important conclusions, we will conclude our discussion for this week. I look forward to seeing you next week as well, and starting next week we will start developing some more detailed solutions for these equations using the concept of transmission line equations. So, till then, have a great day, and I look forward to seeing you next week. Bye. Thank you.